Follow on for last week's talk, which was about moving galaxies. This is about black holes in small places.
Thanks very much for having me. This is probably the last talk I'll give before my life changes dramatically, so I'm super excited to be here. I heard you had a talk on dwarf galaxies last week, so that's very timely. I'll be talking about two completely different aspects of dwarf galaxies. One that has interested me since my thesis, which is whether or not there are black holes in the centers of dwarfy galaxies and how the demographics of black holes change as we go to the lowest masses. And then for a radically different density regime from the absolute most dense place in the universe, I'll transition to these super low surface brightness galaxies that are 10 to the 8 solar masses of stars spread out over the size of the Milky Way, these ultra diffuse galaxies. And I'll start with a philosophical comment about which I have nothing deep to say, but I do think it's quite amazing that in this dwarf regime, and here I'm thinking about galaxies that are smaller than the Large Magellanic Cloud, so a few times 10 to the 9 in stellar mass or less is typically what I mean when I say dwarfs. You can have things like ultra-compact dwarfs, which have something like 10 to the 7 solar masses of stars in, tens of parsecs. Nature knows how to make those. And nature also makes these incredibly diffuse things. And I'm sure if we could understand the formation paths of both, we would know more about hierarchical structure formation. But I don't understand the formation paths of both. So that's why we all stay in business. So I thought I would start my talk with the black hole end of things. And this is, as I said, work I've been thinking about for a long time, but most recently in collaboration with Amy Rines and Chris Pardo and Andy Gould. So my thesis advisor's thesis was, I think, really the first in the mid-90s to show that basically all massive bulge-dominated galaxies harbor supermassive black holes at their center. And he could see this already just using accretion to trace whether or not they're black holes. And he saw evidence for accretion in such a high fraction of massive galaxies that it became clear that basically most, if not all, massive galaxies have black holes at their center. Since then, of course, with the Hubble Space Telescope and then advances with AO from the ground, we've gotten lots of, sorry, this is not showing up so great, but this is just the black hole mass now measured dynamically versus various probes of the potential of the galaxy, here the velocity of dispersion. And we know that there's a correlation then between the central black hole mass and the dispersion or potential of the galaxy.
Is that the velocity where it's out, where it's flat?
This is a velocity dispersion, not a circular velocity, because these are hot stellar systems. So it's about a square root of 2 less than the circular velocity typically. The hard thing, the question we didn't know the answer to, and still don't know the answer to, is as you go to lower mass galaxies, do you continue to harbor supermassive black holes? And I think your talk last week was about star formation in dwarf galaxies. That's completely the bane of our existence if we're looking for evidence of accretion. It completely masks the emission signatures that we typically rely on to tell us that there's an accreting black hole. Or if you want to try and use the dynamics of the stars or gas at the center of the galaxy, of course, the black holes are getting smaller. And so our ability to resolve the region of the galaxy where the gravity of the black hole dominates becomes very limited with current technology. And so it's actually quite challenging to address what happens to the demographics of black holes in low-mass galaxies. We're interested not just because we want to know the answer, but also because we hope that dwarf galaxies don't do much in their lives. They don't merge that much. They sort of sit around. They're not so good at making stars. So looking at the black holes in the low-mass galaxies, it's like the dregs of the seed black holes that were formed early that eventually eventually grew into the supermassive black holes that we know and love in M87. And so the idea is if we can ask questions like, what's the smallest supermassive black hole that I can find? How often do dwarf galaxies have black holes at their center? That this can provide some indirect hints about seeding mechanisms, hundreds of millions of years after the Big Bang. And so just briefly, there are kind of three flavors of stories that theorists have come up with to possibly seed supermassive black holes. The first is the one we're all very familiar with because we see it today, is the death of massive stars. So that makes 10 solar mass black holes, maybe 40 solar mass black holes. Today, the first stars we think may have been much more massive, so you might be able to make a 100 solar mass seed through the collapse of the first stars. This, of course, is somewhat problematic if you want to explain the 10 to the 9 solar mass quasars that we see at redshift 6. And so theorists got more creative. They came up with a second family of models in which the gas basically directly collapses into a black hole. If these models work, they could make 1,000, 10,000, 100,000 solar mass seeds directly. Of course, you still have to get rid of the angular momentum, you have to keep the gas from fragmenting, and you have to shield it quite aggressively and keep it cold. So it's not completely clear that this channel works, but it would, if it does, would make you much more massive seeds. And the third route, which actually has had a renaissance in the last few years in the literature, is that you form a dense cluster of stars, and then you make one massive black hole through the death of a massive star, and then you just get a dynamical runaway in the center of the cluster, which could also build you as something like 10 to the 4 solar mass seed black hole in, billions of years, depending on how dense the cluster is to begin with. So those are the families of models that we have at least thought of so far. And as I said, one boundary condition on which seed process is most important is that you have to be able to make 10 to the 9 solar mass black holes very quickly. It's hard to do that if you start with 100 solar mass seeds. So theorists like these heavier seeding mechanisms. The other type of constraint we can place, which is indirect, is the game that I want to talk about, which is looking at the demographics of black holes in low-mass galaxies today. And this is just a cartoon of how it could put some kinds of constraints on how the seeding works. So if you imagine making massive seeds, either through the direct collapse channel or through dynamical runaway in clusters, what you're imagining is that each black hole is more massive, but it's much less likely that that will happen in a given halo. And so you seed fewer halos. Whereas the death of massive stars presumably happens in every halo, so you get 100 solar mass seed in every halo. And then you do some magic merger trees, or you put it into a lustrous, or whatever your favorite way of tracking dark matter halos is, and you can actually predict different distributions of black hole mass as a function of stellar mass, depending on how you seeded the halos very early in cosmic history. And of course, there's any number of assumptions that go into propagating between the seeds and the present day. But ultimately, what we as observers would like to provide is what fraction of dwarf galaxies harbor black holes and what is their distribution of mass. So that's the goal. As you'll see, we're making some progress, but we haven't achieved that goal. So how do we go about just figuring out where the black holes live in the dwarf galaxies? Of course, the best way to determine whether or not there's a black hole is through dynamics. So you would like to be able to say the stars or gas in the center of this galaxy is moving so fast that there must be a very dense object, too dense to be explained by any other astrophysical phenomenon. As I already alluded to resolve the relevant scales, which are fractions of a parsec for these low-mass black holes, requires that the galaxies be very nearby. So the first place people looked for black holes in low-mass galaxies was M33, which is a nearby neighbor of Andromeda. And there's an upper limit of 1,000 solar masses or less for any massive black hole at the center of M33. And that came out in 2001, very soon after the discovery papers of the black hole sigma relation. And so people basically at that point said, okay, it's solved. If you have a bulge, you have a big black hole. If you have no bulge, if you're one of these wimpy late-type spirals, you have no black hole. The problem was we also had basically the same galaxy. This is NGC 4395. It's also a late-type spiral galaxy, also has a nuclear star cluster. Pretty much the same stellar mass as M33, just a little bit further away, 4 megaparsecs away. And since 1989, we knew that it harbored an active galactic nucleus. And we now have a relatively good guess for the black hole mass, which is 10 to the 5 solar masses. So M33 seems to have no massive black hole. NGC 4395 has one. What's the complete demographics of this population? There's not very much more that you can do with dynamics. This is almost everything in the published literature trying to constrain supermassive black holes in galaxies with masses of less than 10 to the 9. I've left out a couple globular clusters, but I'm not going to talk about the controversy of whether or not there are black holes in globular clusters today. There's a couple measurements. NGC 404, a small S0. NGC 3621 has an upper limit of a few 10 to the 6. NGC 205 and M33, there's a handful, Fornax and a couple other local group dwarfs have upper limits of a few 10 to the 6. And then there was this super exciting recent paper by my friend Anil Seth in this ultra-compact dwarf galaxy. So these ultra-compact dwarfs are, again, 10 to the 7, 10 to the 8 solar masses in stars. This guy's 10 to the 8 solar masses in stars and a 10 to the 7 solar mass black hole. We think that UCDs form as much more massive galaxies and then get stripped. So we don't actually think that their history is quite the same as these galaxies who have been low mass their whole lives, but it's an interesting addition to the story. So that's pretty much everything that we can do, literally everything that we can do with dynamics. So we're kind of stuck with less direct indicators of the presence of black hole that come from accretion. So, 10% of local galaxies show signs of an accreting black hole. We can play the same game with dwarf galaxies. This is the most recent work that I was involved with, led by Amy Rines. And she just went into the Sloan Digital Sky Survey and took all the dwarf galaxies, 25,000 of them, with masses LMC mass or lower, and she looked at their optical emission lines. Okay? These are these well-known BPT diagrams. This is basically just asking what is the spectral shape of what is exciting the gas, and if you're star forming, of course you live over here, and if you have a much harder ionizing spectrum, then you have a wider range of ionization states, and you live over here if you're an accreting black hole. So a handful of these 25,000 galaxies showed some signs of accretion, and a small handful of those showed broad emission lines, which we interpret as gas moving in the potential of the supermassive black hole. So Amy and her collaborators have now been actively following up this sample. This is Vivian Baldassarre's thesis, one of the most extreme objects in the sample. We guess has a black hole mass of only 50,000 suns, and if you want to know how we guess the black hole mass, we can talk about it after, but there's probably an order of magnitude uncertainty in that guess. But it's got a well-detected X-ray source. It's got clear high ionization lines. We're pretty confident that in this source it's powered by accretion onto a black hole. One of the things I want you to notice is that this X-ray luminosity is actually quite low, a few times 10 to the 39. And the width of this broad line is actually not so broad. You know, you think about quasars, you think about 4,000, 5,000 kilometer per second lines. This is 800 kilometers per second. So to use accretion signatures as an indicator of the presence of a black hole at these low masses, whatever we do, we're right up against the boundary of where stellar processes could also be what we're seeing, right? I mean, it's easy to imagine one or a few low mass X-ray binaries giving you a few times 10 to the 39 in the X-ray, and supernovae and other sorts of stellar winds can also give you a few hundred kilometer per second broad lines. Yeah.
Can you estimate the rate of accretion in terms of solar mass?
Well, we could, but there's an order of magnitude uncertainty in the mass. So, I mean, we're talking about less than a tenth of the solar mass per year of how these things. But they're all typically, you know, more than 10% of Eddington, because otherwise we wouldn't see them. So just to make this point about stellar contamination explicit, here are some of the broad H-alpha lines from Amy's original paper, and some of them are nice and symmetric, but some of them are asymmetric and weird. And even at the time we thought, I wonder if these are AGN, or are we maybe being contaminated by supernovae? So what we did is we got multiple epochs of spectroscopy, particularly for the guys who we had selected to have broad emission lines, but whose narrow lines live in this star-forming part of the BPT diagram. So we were particularly suspicious because they are very vigorously forming stars. They're very blue in color, and indeed, all of them had their broad emission lines go away when we got spectra 5 to 10 years later. And so those were really all powered by stellar explosions, not by accretion onto a black hole. So this is nice in the sense that we've cleaned up our sample. We also found at least one really cool type 2N that has a sort of 20-year fading from a really lumpy broad line down to nothing. So this was fun, but it just really highlights why it is so challenging to determine whether we're looking at accretion or whether we're looking at stellar processes in this regime. So of course, the next big step to go from, yes, we found some AGN in dwarf galaxies, to answering the question of how seeds are formed is to really try to understand their incompleteness. And this is a hard problem, and it's one that we're working on now. It's what I had promised to do for the last chapter of my thesis, so now, 20 years later, we'll see. Also, just an advertisement. Jeremy Bradford is a graduate student working with Marla Jiha, and they've started to look at the H1 properties of the galaxies in Amy's sample. And one of the kind of fun, tentative results is that there seems to be, so one of the things Marla has shown is that you are never a red dwarf galaxy if you live far from an L-star neighbor. You can only turn red if you have a big galaxy nearby. Apparently, the other channel to turn red may be to have an AGN. So there are some isolated red galaxies without any H1 that have an AGN. So we're wondering whether it is possible that we're seeing evidence that the black hole is evacuating the galaxy of its gas. But this is pretty preliminary, so stay tuned and look out for Jeremy's thesis. Okay. So I feel quite confident from NGC 4395 and from everything in Amy's sample that there are black holes in dwarf galaxies, but we still have not addressed the question of how often they occur. One way we can increase our statistics is to go to higher redshift. Okay. So use very deep field data to increase our volume. Instead of going wide with Sloan, go deep And in this case, this was work led by Chris Pardo and Andy Goulding. We used this Aegis field that has deep 2 spectra, so all the objects in our sample we know the redshift for, and somewhere between 200 and 800 kiloseconds of Chandra data. Okay, and so there were 600 galaxies with spectra, with masses below the LMC that we investigated, and something about like 10 of them had very robust X-ray detections. And this is just showing now the range of X-ray luminosities. So again, anything from a few 10 to the 39 up to 10 to the 42. So again, you ask, well, how do you know it's not just star formation? And we do what everyone does. We take the local relationship between the luminosity that you get from high mass X-ray binaries in a star-forming galaxy and the star formation rate, which was calibrated by Brett Lemmer. And we ask whether the X-rays fall above that, and indeed they robustly fall quite a bit above the expectations from pure star formation. Of course, this relationship was calibrated for more massive galaxies with solar metallicities, so we don't know the scatter very well in this relationship for low metallicity. If you get a lot more high mass X-ray binaries as you go down in metallicity, this could cause some of the objects in our sample, but taking this relationship at face value, the majority of the objects in the sample are in fact powered by accretion. We also have beautiful deep 2 spectra, so we can again ask where they fall in these ionization diagrams. Unfortunately, we don't have all 4 strong lines for all of them, but their ensemble of line ratios puts them in the AGN part of this diagram. So again, consistent with the idea that they are in the majority powered by accretion. And just because we could, and because Rachel Somerville is awesome and down the road, we compared with her model expectations for the AGN fraction at these redshifts, around a redshift of 0.5 for the lowest mass galaxies. So our measurement is in blue, and her model, for reasons we'll probably never understand, seems to agree with our measurement. So we figured we'd publish that. But all joking aside, I actually think there's quite an opportunity now. We have a variety of different constraints at different redshifts on the AGN fraction in low mass galaxies. And if we then compare with different models, with different seeding mechanisms, we may be able to rule out at least parts of the parameter space as the number of constraints goes up. So I'm almost coming to the end of the first part of my talk. Just to recap, we do find accreting black holes in dwarf galaxies. We know that not all dwarf galaxies harbor black holes because M33 doesn't seem to have one, but we know that some do. We are just starting the process of really digging into our incompleteness in optically selected samples and complementing the low redshift 0 samples with higher redshift deep field to try and get more statistics to understand the demographics of black holes in these galaxies. But can I answer the question that I set out to answer? Well, the best job I think done so far was done by Brenton Miller and Ellaby Gallo in Michigan, and they have a survey, a Chandra snapshot survey of low mass red, well, all mass red galaxies. Working with red galaxies is nice because you eliminate the contamination from star formation and high mass X-ray binaries, so you only have to worry about the contamination from low mass X-ray binaries. So taking that out and just looking at the distribution of X-ray point sources as a function of stellar mass, they placed some constraint on what fraction of the 10 to the 8 to 10 to the 9 solar mass galaxies contain black holes. So this is almost completely degenerate with the distribution of accretion rates onto those black holes, but not completely. And so we're able to say that our best guess is that something like 70% of galaxies in this mass range of of 10 to the 8 to 10 to the 9 solar masses harbor supermassive black holes. Brenton ended this paper with a discussion of how you would need to improve the X-ray data to get better constraints, and he said, you know, we need a PSF of 0.1 arc seconds. So we are actively working to get larger samples, but we'll see if we can do better. What can we do to do better? Let me just go to my next step slide here. So I think there's a lot of prospects actually for dynamics. ALMA is just getting to a point where it has 0.1 arc second resolution, and many of our low mass galaxies are gas rich. And so I think we will be able to push out a little bit further and to a different subset of galaxies and get dynamical masses using ALMA. We've got a couple pilot programs going now to demonstrate that this is possible. 30-meter telescopes, of course, will allow us to get dynamical black hole masses for 10 to the 5 solar mass black holes all the way to Virgo. So that's a much, much larger volume than the 5 megaparsecs we can do now. And that will really revolutionize this field. Also, exciting prospect is the James Webb Space Telescope and the possibility that we may directly measure black hole seeds forming. I'm cautiously optimistic this may happen with JWST. I'm convinced it will happen with W first because of the wider area. So I think in the next 10 years we will be robustly detecting accreting black holes of 10 to the 5 to 10 to the 6 solar masses at redshift 6 to 8. And then I know you've had a talk recently from Subi Ghazari. One of the completely complementary ways to probe black hole demographics is to use tidal disruptions, because you don't have to wait for the black hole to actually accrete gas. They're all going to eat a star eventually. And so as Pan-STARRS is getting mature and LSST is coming online, I have hope that we will get new constraints on the demographics of black holes and low-mass galaxies using tidal disruptions. So that's the main punchlines I wanted to give you about black holes and dwarf galaxies. Before I get to the ultra-diffuse galaxies, I'll just see if anyone has a burning question. There's 1 and 2.
So I have a question about, you have, M33 doesn't have a black hole.
Right.
It's a very small one. And similar galaxies, or apparently similar galaxies that do have black holes, has anyone done work to try and figure out if there's like a marker or indicator or something to enable you to distinguish between spectral line widths or whatever? If you could say, these guys.
Well, I mean, the spectra certainly look different. In GC 4395, the black hole is actively accreting. So we see the AGN. So that's how we know it has a black hole in that case. But that's a transitory thing. The stellar masses, the colors, the star formation rates, the environments of the galaxies in Amy's sample don't distinguish themselves from the dwarf galaxy sample at large in any way, except maybe that second order trend that Jeremy might be pulling out, that you could be isolated and red if you have an accreting black hole. That maybe is the one exception, but otherwise, no.
What fraction of them are X-ray sources?
I mean, that's just a question of how hard you look. So in my thesis sample, which we selected on black hole mass, we detected all of them in Chandra, but those were at the more luminous end. With Amy's sample, we've published 12 of them with 10 to 20 millisecond Chandra observations. There's nothing terribly surprising about their X-ray relative to what we see in the optical. Kind of in keeping with what you might expect, get a little bit more X-ray per UV photon as you go to these lower masses. I think happens if the accretion disk gets hotter, so we can see second order things like that, but we don't see much from the X-rays. In the case of NGC 4395, which is very close, it's wildly variable in the X-ray. And so one of the constraints of the black hole mass does come from looking at the variability.
So I guess one question that I've been thinking about a lot with this whole topic is, so in 2006, Frank Groves had a paper on diagnostics for finding agents in low metallicity systems. And basically what he showed was that BPT diagnostics, especially the nitrogen version of it, are pretty severely biased towards at least solar or supersolar metallicities. If you want to find an AGM with metallicity below, say, half solar, it's not going to show up on the BPT diagram. Or it'll show up in the star form of the BPT diagram. So my question is, given that, and generally N2 over H alpha is used as kind of a proxy for metallicity. So that's kind of so basically my question is, if you are using BPT diagnostics to find AGNs, then you're sort of preferentially picking out systems which are not particularly low metallicity. And
So I'm just going to briefly
sure.
beg to differ with you.
Okay.
That's NGC 4395,
Right.
which is a 1/3 solar
Yeah.
so thing, depending on who you want to ask. So there's a lot of space up here before you run into the extreme star formers over here, where I think you'd have to be 100 solar before you start to worry about overlapping stars.
Well, I mean, that was just the result of that particular paper.
No,
But I guess my
this
question
is
was,
this is where they live in that particular paper,
for what that's...
where some solar AGN live. 4395 was like his
Yeah.
test case.
But again, that's sort of roughly half solar. So my question is, like, for example, like
Well, the stellar masses of the galaxies we're looking at are not so low that they'd be much less than a fraction.
So that was my question is, where do these fall on the mass metallicity relation? And are they generally higher than what you expect for a given stellar mass? And if so, what does the effect of chemical evolution have on the question more broadly? Is if you have more chemically evolved systems, even if they are dwarf galaxies, how can you say, like, can you sort of quantify or estimate how much sort of secular accretion the black holes have gone through? And then that leads to the question of sort of how representative of the initial seed are the black holes? That's my question sort of more broadly.
Yeah, so it's hard to do this because no metallicity scale is absolute, and because there is an order of magnitude scatter in the mass metallicity relation anyway. We have not tried this with Amy's sample. We have tried it with my thesis sample as part of the thesis of one of my students. And we didn't see any evidence that they were in any way deviant for their mass. So they didn't systematically have higher metallicities, but keep in mind that using Brent's models, which you have to make assumptions about the AGN properties, it's pretty hard to line up with just mass metallicity that's been done for the star-forming galaxies, right? So even though they've done their best, and they're a lot smarter than we are, that's a really hard game to play.
Yeah, and I guess that's sort of...
But I guess I would say you really would have to be thinking about maybe 10 to the 7 solar mass galaxies before I think you'd actually be biased, because there's just an awful lot of room up here where there are no star-forming galaxies, at least at redshift 0. So I don't think it's a real concern that we're somehow biased in our selection.
Right. Yeah. I have a second question about it. It's related to that, but I'll ask you.
Okay. Let's do one more question, then I'm going to do my second part.
Quick question. So there's all these talk about these black holes sloshing around depending on when you have merged. This is usually at larger galaxies. So do you have the resolution here to see it at different wavelengths, whether there's an offset between, say, the X-ray and the optical center mass, or these are too far away and you can't?
We would love to be able to say we found something offset. We haven't so far.
part of Amy's thesis was this galaxy Henice 210, which is a dwarf starburst galaxy. And she has VLBI radio measurements that line it up with the X-ray source that she originally identified to think that it's an accreting black hole. We have not pushed hard on the radio, partially because they're not that bright in the radio. So far as our HST plus Chandra measurements go, they all seem to be at the centers of their galaxies. The piece of my talk that I skipped is the really exciting prospect to me that was opened by this detection of a black hole in an ultra-compact dwarf. So that, I think, proves that a lot of the lower mass black holes are living outside the centers of galaxies because they started their life in a small galaxy, they got eaten, but the dynamical friction timescales are infinite, so they don't make it to the center of any new galaxy. They're just out there in the halo of, maybe there are 10 to the 3 to 10 to the 4 solar mass black holes in the halo of the Milky Way. In the Virgo cluster, there are probably free-floating 10 to the 7 solar mass black holes, and we have no census of those to date at all, the Zoom type. So one of the things I certainly hope we accomplish in my lifetime is a complete census of the off-nuclear black holes. I'm pretty excited about that. I think we'll make progress. Okay, so I'm going to completely change gears now and tell you about the least dense dwarf galaxies. And this is a slide made by Peter Van Dockum. And everybody here is of the same physical scale. So this is Andromeda, a galaxy we know and love. And this is M33, a galaxy we've discussed today. And this is a 10 to the 7 or 10 to the 8 solar mass galaxy, which is similar in size to the Milky Way, but has only these 10 to the 7 solar masses of stars. So extremely, extremely diffuse, low stellar density galaxies that we've known about for a long time, but there's sort of been a renaissance in studying these things as imaging surveys get to the point where they can really probe the low surface brightness universe in a different way. So this is going to be work mostly led by my graduate student Johnny Greco and really enabled by the new survey that we're doing at Princeton in collaboration with the Japanese astronomical community using the Hyper Supreme Camera survey. So I want to spend a little bit of time introducing you to this survey and all of the super cool things that we're doing at low surface brightness, and then tell you a little bit about our search for ultra-diffuse galaxies. So we're using the Subaru telescope, which is on Mauna Kea and is here. If you've ever had the pleasure of being there, you know that it was very clearly built by the Japanese, and everything is just larger than life at Subaru. So here's a picture inside the telescope, and what makes Subaru really unique, of course, is that it is prime focus, and so unlike the majority of 8-meter class telescopes, it is really perfect for surveys. It has a very wide field of view. And we are exploiting this in what we are calling SUBIRE, Subaru Measurements of Images and Redshifts. This is a 2-part survey. The first part is underway now, using the Hyper Supreme camera, which I'll introduce to you in the next slide. And the second component will be spectroscopic follow-up using the prime focus spectrograph that we're currently in the process of building. Okay, so this is, we like to think of it as Sloan at redshift 1 to 2. Here's the Hyper Supreme camera with a 1.8 square degree field of view. It's like 80-something CCDs. And it's getting close to LSST. So this is, for us, in many ways, LSST practice. Robert Lupton has been doing all the image processing and pipeline work, which is all preparatory for what he'll be doing for LSST. And the survey that we're doing with this very wide area capability has 3 layers. It's a wedding cake. The wide area will be 1,400 square degrees to a depth of 26, 5 bands, G, R, I, Z, Y. Then there's a deep area designed to study redshift 1 to 2, which is 30 square degrees, 1 magnitude deeper, and includes some narrowband imaging. And then there's an ultra-deep component, which is 2 HSC pointings that actually has, I believe, 4 narrowbands and hopes to get to depths of 28 if indeed we can achieve that depth. So if you are one of those kinds of people who carries all these deep fields in your head, this is a map of where our survey areas will be. So it's largely equatorial. There's one northern field. And the deep fields are lined up with all the famous deep fields so that we can get lots of multi-wavelength data. So this is what we're doing. We're sort of a year and a half into the 5-year survey. So we've got about 300 square degrees of wide data processed now, and the first public data release, which I think was 100 square degrees, happened in February. So please, if you want to see some gorgeous images, please take a look at our public data release. What makes this powerful? You've got to compare your survey to the full moon. Okay, you want a fast, wide, and good spatial resolution all at the same time, and HSC really has been delivering that. So these are some examples of the previous large area imager that was on Subaru, the Supreme Cam, and this is the field of view of HSC in comparison. So we can really cover large swaths of the sky. Our sort of favorite promotional image is this picture of Andromeda. So this is one pointing with HSC. In comparison, the FAT survey, which was done with HST, took many hundreds of pointings to cover a quarter of Andromeda's disk. Of course, they get higher spatial resolution, but we don't do so badly. So let's just zoom in on Andromeda's disk here, and you can just see kind of how beautiful and rich our data are. HSC has just been delivering spectacular image quality, very uniform across the field of view. Routinely, we can achieve 0.5 arcsecond seeing. And this, of course, is a super fun thing you can do, comparing the depth of Sloan. So here are 2 galaxies in Sloan, and here's what they look like with HSC. So just remarkable sensitivity to low surface brightness and faint features. So what are some of the fun things that we've been doing? My postdoc, Andy Goulding, has put together a sample of Y-selected AGN out to a redshift of about 0.9 within the HSC fields. It's about a couple hundred square degrees, many thousands of accreting black holes, and he is trying to answer the long-standing question in the AGN community is whether or not merging of galaxies is responsible for triggering accretion onto black holes. This is just a promotional figure showing how beautiful some of the mergers are that he's finding. And I can now give you a preliminary result, which is that if you just look at the fraction of galaxies that are actively accreting as a function of their merger state, we do see that a factor of 2 more accreting black holes in ongoing major mergers than in inactive, non-merging systems. So there does seem to be an excess of AGN activity in merging galaxies, similar to what's been seen at a lower level for lower luminosity systems at redshift. That's one of the fun things you can do. This is work led by postdoc Song Wong and Alexei Leothod. So again, an application that really exploits the low surface brightness sensitivity of HSC. This is now the most massive galaxies in the universe. All of these galaxies have the same stellar mass within 10 kiloparsecs. But as you go from the top of the slide to the bottom of the slide, you may notice that you get larger and larger halos, stellar halos around these galaxies. These are the isolated galaxies, and these are the galaxies that live in the centers of rich clusters. And so it's very clear that something changes for massive galaxies when they live in dense environments. Here's the radial profiles. Again, if we normalize the stellar mass within 10 kpc, we can see that the galaxies that live in high mass halos, this is the average in the red line, have much more extended envelopes than those that live in low density environments. So they've really been bombarded at late times, they've eaten a whole bunch of schmutz, it's accumulated all the way out to 100 kpc. So this is another fun result that you can only really do when you have the exquisite surface brightness sensitivity afforded by the hyperscreen. Okay, so that gets me back now to the main purpose of my talk, which is to try and understand the formation of these ultra-diffuse galaxies. And like I said at the beginning, we've known about low surface brightness galaxies for quite some time, and even these red ones were uncovered by early surveys in Virgo by Sandage and Bingley and collaborators. And then Julianne Del Canton did her thesis at Princeton to study low surface brightness galaxies in the 90s, so we figured enough time had passed, it was time for someone to revisit this topic again at Princeton. And just to remind you, we're talking about 10 to the 7 solar masses of stars spread out over Milky Way sizes. This field was really rejuvenated because Peter Van Dokkum has this Dragonfly survey using small aperture, very small aperture telescopes, but exquisitely sensitive to low surface brightness things. And they uncovered about 1,000, well, he found 40-something, and then Coda et al. 2015 went back and found about 1,000 of these extended low surface brightness galaxies in the Coma cluster. So people got really excited about what were the physical mechanisms that cause these galaxies, which have such large physical extents, running out of time, to be found so preferentially in rich environments. And so people have now looked in Virgo and Fornax and Perseus and a handful of low redshift clusters. There's evidence for at least a couple of these that they live in extremely large dark matter halos. I mean, that their size probes their dark matter halos. So they have Milky Way-like halos and are extremely anemic in stellar mass, very, very high mass to light ratios, and correspondingly very high globular cluster counts. The problem is, main question is, how do you make them? So Julianne's theory was that, well, there's got to be a high angular momentum tail to the halo distribution, and those galaxies are just naturally going to be more spread out and more diffuse. So that was her motivation for looking for low surface brightness galaxies. But because all of these UDGs have been discovered in rich environments, an alternate possibility is that they fell into a rich environment early and really got completely stripped of their baryons early and became independent. And the question is, do both of these formation channels happen, or is one preferred over the other? And to answer it, you really need to go beyond just having a cluster sample. You also need a field sample. And this is where HSC comes in. And so Johnny, my graduate student, has been going through all of our wide data so far. I won't go through the details, but he's been very successfully uncovering extremely low surface brightness galaxies. Of course, we don't necessarily know the distance, but we're finding things down to surface brightnesses of 27 magnitudes per square arc second. I'll show you some examples. Believe me, there's a galaxy in every single one of these snapshots, and in some cases they're very clearly in groups and poor clusters, and so that gives us the physical sizes. So we're finding lots and lots of things, red things in this UVG regime, and they do seem to be clustered around their groups. At the same time, we're finding lots of other fun things. A bunch of them are lumpy and blue and isolated. Some of them seem to be semi-resolved and very, very close to us. And then, as a side product, we're finding extraordinary tidal features quite far from their host galaxy. I don't know if you can see this, but it's like a whole ring of tidal fluff. So Johnny just recently published a paper on this guy. This is a 20 kiloparsec tidal feature, we think, around this absolutely gorgeous caustic post-merger galaxy. So I'm out of time. So I will just flash up my UPG conclusions and questions.
Have any of the ultra low density, cell density on this gravitational lens?
You mean back? So, no.
Quantified backups.
You mean strong lensing, right? No, but there is a paper in the literature performing stacked weak lensing for all the UDGs that were found by that Vandenberg
So I
paper.
call it little backups.
Right, so just asking, do we see, on average, some distortion in the background galaxies that give you a handle for the average dark matter halo mass? And the punchline from that paper is that most of the halos, that most of the UDGs don't live in Milky Way mass halos, but instead live in 10 to 10 to the 11 solar mass. So not anywhere near as extreme as that one guy that I flashed very quickly. That seems to have a Milky Way mass halo.
Is there still considered to be a deficiency of dwarf satellite galaxies?
Yes.
And does this work at all?
Yeah, so the missing satellite problem, has morphed and been given lots of other names like too big to fail. But there still seems to be a number of problems, but matching observations of satellites to theoretical expectations. These galaxies, so one obvious spin-off for Johnny's thesis is to look at low surface brightness satellites around nearby galaxies and see if we uncover more than we would naively expect, although we're not going to get down to the kinds of 10 to the 5 solar mass galaxies that you can do in Milky Way studies. We think these have much more massive halos, so they don't directly solve the problem of the missing satellites.
In those diffuse galaxies, do you have any measurements of what type of stars are there? Can you get a spectral, or is it just too faint for you to
So sorry, I went too fast, but the deepest spectrum to date is this 33 hours with Keck that was published by Van Dokken's group. Just to give you a sense, they're having a, pretty decent signal to noise for 25 magnitudes per square arc second. That's 33 Keck hours. The kind of constraint you can put on the stellar population is it's pretty old and it's slightly metal poorer than more massive galaxies. There is now an Arecibo detected sample of low surface brightness things. For a long, long time, the Arecibo community has been wanting to find dark galaxies. Also with the motivation of understanding the missing satellite problem. So maybe we don't find them in stars, but maybe we can find them in phase one. And they just put out a paper with 30 or 40 H1 detected galaxies with very, very low stellar densities. And those probably have younger ages. They probably have ongoing star formation, and they probably live outside of rich clusters. So some of our blue guys would be like that as well.
So I have to ask, LSST is supposed to be very good at finding Pokemon objects. Can you do Pokemon objects? Any
So,
part of it?
we had a lot of discussion of doing that with HSC when we were designing the survey. The question really is the cadence of the wide data. And at least for the current 300 square degrees, we have been prioritizing completing the data so that we can do the really, the big money sciences, the weak cleansing and shear measurements and getting a handle on it. I think to really do the Kuiper Belt stuff, you need to take at least one of your epochs well separated in time from the others. So maybe as the survey matures, we'll start doing that. But for now, we're really trying to get to full depth over sort of the 500 square degrees so that we can compete with DES and get the papers out.
Does the data become public?
Yeah, so we've already had our first data release in February.
100 square degrees.
It's something like that. But it was more than half of the data that we had when we released it. We've just been accumulating more. So there was a year-ish lag there, which was mostly because the software people were working on the pipeline products. The pixels are not just released, but all of their catalogs are also released. So we're hoping that people will do all kinds of fun stuff with it. The catalogs still have some better.
Hope there are no more further questions. Let's thank our speaker again.